Welcome to another video from Lockdown Electronics with me, Bill. This time we've got a review, and it's a review of an LCR meter, the Ruoshui 4090 Model C, which is here on the shelf behind me. And an LCR meter is a specialist kind of measuring instrument, so let's take a closer look, and in doing so let's try and answer, I guess, three questions really. Firstly, what is an LCR meter? Secondly, how does it differ from a multimeter, and is it the kind of thing that would be any use to you? So let's take a closer look. Here's the Ruoshui 4090C LCR meter then, and just talk you through the general features. It's a fairly large bench unit, mains electricity powered, and obviously you've got this handle so you can position it in several positions. Normally it lives on one of my shelves with the display at about eye level, which is quite handy. Lots of buttons. I won't confess to knowing the exact operation of every one. There's quite a lot to learn about the instrument, but essentially when you switch on, and it is a hard switch, so it's actually switching the mains. When you switch on, it doesn't take very long to boot, very quickly boots into that setting. And first thing to note is we've got 4 connections, and they are BNC cables. I'll just take that off for you. And the center connector of the BNC cable is what does the measuring. The screening is just an attempt to minimize the stray capacitance between the 4 measuring leads. Now we've got them attached to 2 Kelvin clips, like so. And if you're not familiar with Kelvin clips, this is a 4-wire measurement method, and so the pieces of coax from the red connectors here go into this clip. One of the centers is connected to one side of the crocodile jaws, and the other cable is connected to the opposite side. So when they make connection on something, you've got essentially 2 wires feeding to that point, and they're both screened right up to the point of the jaws. Now if I force that into capacitance, if it'll do it for me, there's capacitance, and if I just put the leads together, you notice it's already measuring the capacitance of the leads, small though it is, and if I move them a bit closer we get nearly a picofarad. So one of the things you can do is to calibrate, and you hold the calibrate button and it will now calibrate. Now this is going to take a few minutes. Open there means the 2 clips are separate and you should keep your hands away from them. So I'm just going to speed through this. And there you can see it's saying calibration is okay for open. Now what I'm going to do is I'm going to short out the 2 leads like so. I'm going to keep my fingers well away from them again, and I'm going to press and hold calibrate again. And it's detected the short condition between the 2 probes, the 2 Kelvin clips. So I'm now going to let that run. So we'll just fast forward through this, as I'm sure it's rather boring to watch. So it's coming to the end of its run. It should beep in a moment. There we go, right on target. So that's calibration now complete. And so now what we can do is have a look at some of the features of the instrument. Now it is exactly what it says on the tin. It's an inductance, capacitance and resistance tester. So in one sense it's more limited than a multimeter, but it actually, in my experience, this one is considerably more accurate. So let's have a look at some of its capabilities. And I think one of the first things to note is that when you've got say a very small capacitance, this is extremely good at giving you an accurate measurement. So I've got a 15 picofarad capacitor here, and I'm going to just pop that between the probes, and it's telling us it's 15.8 picofarads. We'll come on to what the other bits at the bottom mean in a moment or two, but that's 15 picofarads. So I've got here a 56 picofarad ceramic capacitor, so we'll just see what it makes of that. And there you go, 55.7 picofarads. Now my multimeter doesn't give me a sensible reading on those two capacitors, I guess simply because it's very small indeed in terms of a capacitance, but this meter takes that in its stride. And I think possibly one of the most interesting things about it is if you get something like this is a bit of well, just some jump leads really for connecting between a circuit board. So if I connect up those two pieces of wire, they're not joined, it tells me that it's 5.6 picofarads, something like that. So now what I'm going to do is I'm going to, the cables are actually a pair there, so I'm going to pull them apart. They were 5.6, I'm going to pull them apart about halfway up and just leave them, and we're now 3.6 picofarads. So it's more than capable of measuring the capacitance between two wires running next to each other. So I think that's quite impressive performance. Okay, let's now go on to look at what some of the secondary information provides for us. Okay, most of the time you're probably just happy to know what the capacitance is to a fairly accurate level of detail, but there are some other useful things this thing measures, and actually they're all related mathematically. So X here is the reactance of the component, and if I now step through to D is what's if you like the dissipation factor according to the things that I've read, and this is a unit which is dimensionless. It's actually it's a ratio, if you like, so it doesn't have specific units. Obviously reactance does have. Moving on, Q is the quality factor. Again, that's the second dimensionless ratio, and that's mathematically related to D. Actually D is equal to the reciprocal of Q. Theta here is the phase angle, and ESR, which is the one that most people are interested in, is the equivalent series resistance. That's also related to the reactance and to the dissipation factor. D is equal to the ESR divided by the reactance. So they're all related in that sense, but what use are they? Well, let's take this electrolytic capacitor here. This is 4,700 microfarads. I'm going to put the unit into electrolytic capacitor mode, and I'm going to short the leads out. I have already done this just now, but that's most definitely discharged. So we'll now connect up the capacitor, and I think probably the first thing to note is it produces a reading very, very quickly indeed. It takes my multimeter a while to get its head around 4,700 microfarads. This is presenting us with the information in millifarads, but just move the decimal point and you will indeed see we've got about 4,560 microfarads according to the unit. And if we now step through to the ESR here, it's 0.036 ohms, so it's quite low and probably quite acceptable as an electrolytic capacitor. As electrolytic capacitors get older, you're probably well aware of this, the ESR rises, which causes the capacitor to heat up, which causes the electrolyte to vanish, or worse, to actually come out of the capacitor and do damage around the circuit board. You've probably seen examples of that. But what is quite significant here, this is the kind of capacitor that you would use on, let's say, the smoothing circuit in a power supply, and currently the unit is set at 1 kilohertz. That's the frequency, the AC frequency that the unit is using to test the capacitor, but we can change that frequency. So I'm going to step right through until we get to 100 hertz, and the reason I've picked up 100 hertz is because that's exactly the kind of frequency this capacitor would be working at. If it was smoothing full wave rectified voltage from a transformer, it would be effectively getting 100 peaks a second, and so the readings we're getting at 100 hertz clearly more significant. So still ESR's quite low, below half an ohm, and it's saying about 4,600 microfarads. So I would say that's a good electrolytic. Now while we're in electrolytic mode, let's have a look at this capacitor here. This is a 4 microfarad, and this was removed from a signal generator which I restored. There is a video, I'll put a link up above to that video. It was the Taylor 65B, and this is a 1940s signal generator, so this capacitor is well over 75 years old, so we wouldn't expect a great amount of it, but it's 4 microfarads, so let's pop that on the test. It was a smoothing capacitor for the supply, so 100 hertz is still a valid frequency to use for the test. So capacitance has gone up, and as you can see the ESR is 33 ohms, way high, so that essentially was just getting very hot and would not have been doing a great deal in the circuit, so definitely needed changing. Okay, so that's capacitance. You've seen small capacitance, you've seen quite large capacitance, and you've seen how quickly the instrument's able to test that. It's also does inductance, not surprisingly. So what I'm going to do now is a little experiment so that we can verify some of the answers that we're getting. So I've got a polyester capacitor here, which I'm going to put that back onto auto mode again now. We're not out of electrolyte. I'm going to connect that up, and currently it's doing a test at 1 kilohertz, but I'm going to and it'll make some more sense in a minute. I'm going to up that to 100 kilohertz, the highest this will do. So at 100 kilohertz we're getting an answer of about 9.9 nanofarads, and we're getting, yeah, the ESR is unimportant here. That's a polyester capacitor. It's good. So we're getting about 9.9 nanofarads. So I'm going to make a note of that. And we've also got an inductor here. This is 220 microhenries. So hopefully the unit will automatically detect it's now been given an inductor. I think because I've changed the ESR it's not, so I'm going to just change that to inductance. There we go. You can ignore the ESR on this particular reading. So we're getting 189.8 microhenries, and that should be 220 microhenries. And in fact, if we now step through back to 1 kilohertz there, we do actually get quite near to 220 microhenries, so that sort of makes sense. But the reason I've gone up to 1 kilohertz is because I want to verify the accuracy of the instrument if I can, and to do that I'm going to put that particular inductor and this capacitor into a series tune circuit, and we'll have a look at the maths for what the answer should be, and then we'll do a bode plot on the scope and see if we actually get an answer which is similar. So yeah, this would be quite a good way of identifying a specific value component if you'd got if it was critically important for a circuit. So let's now just have a look at that information together and then look at the bode plot. Okay, it's a bit of maths, don't panic. So the resonant frequency of a tuned circuit, so that's going to be a capacitor and a coil in series in this case, is equal to the reciprocal of 2 pi times the square root of the inductance and the capacitance. Now let's say the design called for 10 nanofarads and 220 microhenries. If we plug those numbers into that equation, we get just over 107 kilohertz, but our actual measurements are 9.9 and 189, you may remember from earlier, and if we plug those units, those measurements into the equation, we get 116 kilohertz. So it's about 9 kilohertz higher than the design's calling for. And just a quick reminder, those units of inductance and capacitance are in henries and farads. So in the case of these two units, we're going to be 9.9 times 10 to the minus 9 farads, it's nanofarads, and it's 189 times 10 to the minus 6 henries for the inductance. And so we would expect to get a resonant frequency nearer to 116, and certainly if you were going to use this, let's say in the intermediate frequency of a transmitter, you might be worried about 9 kilohertz. That might matter. So being able to know or predict what we would expect the resonant frequency of this circuit to be could potentially be valuable. So let's just move over slightly so you can see the display a little bit better. So on your left there is the baud plot, and I've moved the cursor. Don't worry too much about the left hand cursor, I've just moved it out the way. So the cursor there is showing I've got it actually at 0 degrees phase angle, and I've got it at what I believe to be the peak of the resonant point on that baud plot. And if you look at the information on the top left for the cursor, you can see there it's saying 115 kilohertz. So within the accuracy of my oscilloscope and various other bits, it's a lot nearer to the frequency predicted by the measurements. It's within 1 kilohertz. And hopefully now you're also understanding why I changed the testing frequency on the LCR meter to 100 kilohertz, because I was expecting the resonant frequency to be something near there. And you may recall also that at the normal 1 or 2 kilohertz frequency, it was a lot nearer to the stated frequency. So sometimes the ability to be able to change the frequency is quite handy. Okay, slightly different camera angle. I just want to look at resistance now, so I want you to be able to see the LCR meter, but also the display of my East Tester ET3240 multimeter. And we're going to, as I say, look at resistance. So I've got a resistor here. It's fairly high value. The multimeter, if I connect the multimeter up, makes of it, let it settle down, about 8.4, shall we say, 8.4 meg ohms. So it's fairly high resistor. Nearly 8.05 meg ohms now. So 8.05, let's call it. Let's see what the LCR meter makes of that. Again, I'll keep my fingers well away, it's such a high value. That's saying 8.03 meg ohms. So in other words, they're both doing a good job there. So let's now try a very different valued resistor. This is the smallest resistor that I have. So I'm going to pop this onto the multimeter and see what we get. Just let it settle down. And it's saying 0.49 ohms, so about half an ohm, something like that. This is a resistor. Got a pack of the resistors. I wanted to use them as a current shunt to allow an Arduino to measure some current. So it's about 0.49 ohms. It's settled down there now. So let's put that on the LCR meter, see what the LCR meter makes of it. And as you can see, that's quite, for a very small value resistor, that's quite a considerable difference. So the LCR meter is saying it's about 0.1 ohms, something like that. So considerably less than the multimeter is making of it. And that's actually because it is a 0.1 ohm resistor, or supposed to be. And this is the advantage of 4-wire method measurement, because the meter is able to put a voltage across the component, and then it's able to use two of the other leads to measure the voltage across the component, and that's much more accurate than a method that involves probe leads, etc. But the good thing about the multimeter is this one, it's actually got the ability to do 4-wire testing. Now I don't have any Kelvin clips for that, so that's just on the 2-wire method, and it's saying about 0.47 ohms, something like that. And I've got these two crocodile clips here, which are attached to the 4-wire method. So I'm going to attach those like so. Oops, so. Appreciate you can't see this terribly well. So I've got them attached like that, and I'm now going to tell the machine to work in 4-wire mode, so we're 4-wire mode there, and suddenly it's starting to agree with the LCR meter. Remember, the LCR meter was saying 0.1 ohms, this is saying 0.09 ohms. Now those are screened leads, I don't have any Kelvin clips or screened leads for the meter, so I'm inclined to believe this, but suddenly we've moved to within 0.01 ohms difference between the two. So another example of the LCR meter is its sort of inherent accuracy, if you like. Okay, there we go. That's a look at the instrument and its capabilities. Okay, well that's it for the review of the Ruoshui 4090 Model C LCR meter. I hope it's made some sense and you found it useful. Now, one of the questions I asked at the start of the video was, is it something that you need? And I guess the answer to that question really depends on what your measurement interests actually are. If you want to measure small inductances and small capacitances and even small resistances very accurately, then yeah, this kind of thing is the tool for the job. You may find that in the normal run-of-the-mill case, a decent digital multimeter will also achieve the same ends. In my experience, digital multimeters aren't quite so good at the smaller capacitance and inductance end of the ranges, and of course they don't all show the equivalent series resistance either of capacitors, which allows you to make some kind of judgment on whether they're life expired or not. So hope you've liked the video. If you have, please click the thumbs up. That's free. It's free to subscribe and it would really help me. Thanks very much for watching. See you on the next video.